This is introduction to modern physics, and we're going to start with quantum physics. So the model of an atom, the one that you usually see in the pictures, is not exactly the one that is lately been discovered and explained. So the planetary one is just the pictures that you often see, but the actual model of the atom has been studied and used to apply in chemistry and biology and in physics. And so quantum mechanics is the mechanical framework that underlines the Niels Bohr's model, and later studied by Heisenberg and Schrödinger and many others, including Einstein. It characterizes simple things such as how the position of momentum of a single particle or a group of few particles changes over time. So if you look at the picture that I have on the right, so the picture that we have on the right, you have a molecule and then you have an atom, and then the atom is made of nucleus, which has neutrons and protons, and they are made of quarks. And so what does the quark mean, and what does the electron mean? So electron is the smallest particle and quarks are the smallest particles. So what are they, and what does it have to do with quantum physics? So they did, as we did with double slit experiment, they realized that the electron can behave as a particle or a wave. So when they started to study it more, they figure out that electron can be described as a wave. So this is where the string theory comes. And in attempt to learn the string theory, they realized that electron is the moving so fast. So it's like a energy, and that energy can be described by with a standing wave. So electron can be moving or vibrating in a certain at a certain level of energy, and that energy can be described depending what kind of energy, how much energy it has. So it can fit like one wavelength or two wavelengths or three wavelengths within the circle. So the circumference of an electron can represent, or the orbital of an electron can represent a number of the wavelengths at which it vibrates. And the electrons in the atom can be placed on into different orbitals. So there can be there are 4 different types of orbitals, at S, P, D, and F. And each orbital can only hold two electrons. So when you've seen this in chemistry, you don't really need to do this for not yet, at least for quantum physics. And so the P, D, and F orbitals have different sublevels and can hold more electrons. So let's say S shell has one orbital only, so you can see right here it's like a sphere, like here it is like a sphere. So it can only hold 2 electrons because one orbital can hold only maximum 2 electrons. And then the P subshell has 2 orbitals, so it has 3. So here is the P, so it has so the P right here. So it has 1 and 2, and the other one on Z, X, Y, and Z. So P shell has 3 orbitals, and each can hold 2 electrons. So together the P subshell can have 6 electrons. The D subshell has so here is the D subshell, very strange kind of form. So the D subshell can have 5 orbitals, so that it can hold 10 electrons, and the F subshell can have I don't know why I made it bold. So the F subshell can hold it has 7 orbitals and can hold 14 electrons. And so for each level, you can have a maximum number of electrons. So this is the energy level. So when I talk about energy level, I mean this is first level, base level, and then you have the second, the third, and so on. So each base of the, like here is the hydrogen atom, and then you can have the first and second and third level of energy. So main energy level can hold maximum number of electrons. So the first one can hold only 2 electrons, the second level can only hold 8 electrons, and then the third one can hold 18 electrons. And it's based on how you write electrons per the sub-level. So it would be like this way. And then you have 2 only for S, and then you have 2S gives you the 8 ones, and then you have P and 3. So P can hold, so 2S can hold, so let me see here. So if you have the S, each one can hold 2 electrons, and S can hold only one of the 2 electrons, right? So that would be 2S. And the next one is going to be 2S and 2P. So 2S gives me 2 electrons, and P can hold 6 electrons, so together gives me 8 electrons. And the third level, is going to be 3S, so it's 3S, 3P, and 3S, 3P, and 3D. So here you have 2S and 2P. Here's 2S and 2P. The third level has 3P, 3S, 3P, and 3D. So it can hold 18 electrons because S can hold 2 electrons, P can hold 6 electrons, and D can hold 10 electrons. So altogether it gives you 18, and so on. Again, this is not, we don't use this in AP Physics 2 for our lessons, but I just wanted to go for you that it will have more sense for you. And I will also include more videos which you should watch visual that you would understand better attached to the description of this video. So electron energies. So here is an example of electron energies. And when they described quantum physics, they realized, Planck realized that, we're going to be talking about Planck Constant in a minute. So they realized that electrons cannot jump from one level to another unless it has exact amount of energy needed to jump from one level to another. So for hydrogen atom, it would be negative 13.6 electron volt needed to change from one level to another level. And then, so each orbit has a specific energy needed to bump that electron out of the atom. So, and depending on what element you're looking at, so the atomic number Z, the number of the protons, so Z is going to be different for every single one of them. So for hydrogen, it's 1, and then for helium, it's going to be 2, and so on. So you can calculate how much base energy it has, and if you give that much amount of energy, it will pump out the electron out of the atom. So that is talking about the energy that electron needs. So I'm going to come back to this one in a minute. There is a video that explains this concept even better than probably I will explain to you. So I'm going to touch on a few videos for black body radiation. And I want to talk to you about the quantum, the Planck constant. So the energy of the photon that bumps out the electron from the shell, the energy of the photon can be described as H times F, and F is the frequency of that specific wavelength or photon that is coming, and H is the Planck's constant. So the Planck's constant is the shortest distance possible, that you cannot go any smaller than that. So if you see like the waves are going from radio waves to gamma waves, and the gamma waves have the shortest wavelength. So the shortest possible would be the Planck's constant that cannot be any smaller than like you cannot go any farther than that. So the energy of the photon can be described by this formula, and F is the speed of light over the wavelength of that photon that is coming. And you can write Planck's constant in electron volts. So it is so if you remember, let me get here to one of the formulas I have here. Here it is. So if you remember the formula for the voltage, the potential difference is equal to the work done to move the charge. So the potential, the energy of the photon, it's like work as well. So it's the charge times the potential difference. So when you have electron volt, that means you take 1 electron charge and 1 volt, and that gives you 1 electron volt. So what is the number of 1 electron volt equals to? Energy is measured in joules. So 1 electron is this much charge, and 1 volt is just this. So if you want to know how much is 1 electron volt, it's 1.6 10 to the negative 19, because the charge of an electron is 1.6 10 to the negative 19. So it's electron times volt gives you 1 electron volt. So coming over here, it shows that the Planck's constant can be equals to 6.63 10 to the negative 34, and then converting it to electron volts, it's 414 10 to the negative 15 electron volts. And then the famous MC squared. So this formula is describing the relationship between the mass and energy, and telling us that it is interchangeable. In other form, like the mass is can be fully converted into energy if you take away the mass as the quantity itself. So the energy or the rest energy of the mass is equal to mc squared, where the mass is the rest mass. So it's the gamma factor times the rest mass. So, and the gamma factor depends on the velocity of an object. So as velocity of an object increases, then your denominator becomes equal to 0, and 1 over 0 gives infinity. So for higher velocity of an object, the mass increases to infinity. So you cannot reach the maximum mass of being infinity. So you cannot have an object moving at the speed of light. So this is my basic explanation to you why. But all you need to know is, I'm not going to touch the videos related to this topic as well. So the rest energy is equal to mc squared, and the total energy on the object is equal to the rest energy plus the kinetic energy of the object. And if you want to calculate how much energy is stored within you, so you can take, without thinking about that you're moving at certain speeds and space and so on. So if you want to calculate how much energy was needed to make just you can take your mass. So the average person is about 60-70 kilogram. So you take your mass and the average adult person. So you take mass about 60-70 kilogram and speed of light 310 to the 8. And that gives you how much energy was needed in order to make you. That means to bond every single molecule and atom in your body to make you who you are. So, and then photoelectric effect. So photoelectric effect is, they notice that when light shines on surface of certain metals, it will emit electrons. So if you have this device, the way it looks right here, so you have a vacuum tube, the light is shining on cathode and emits the electrons. And then if you apply potential difference, so if the electrons have enough energy left after they've been emitted, they can reach the other side, and here comes the current. So in when talking about the emission of the electrons, you need, so the photon is coming a certain energy level, so H Planck's constant times the frequency of the photon that is coming as a light, and you will need the work function or threshold work function. So that work function or threshold energy needed to bombard the electron from the surface. So like this type of energy that we were talking about. So you will need certain amount of energy to bombard that electron from its orbit or its atom. That energy can be calculated as H times F sub 0, and that is threshold frequency. So every single material has different threshold frequency or threshold energy. So how much? So this is how much energy photon has. If energy of the photon is only equal to the energy needed to bombard the electron from the metal, you may not have enough kinetic energy to reach the other side of the vacuum tube. So you have to have enough energy in the photon, so you would not only pull out the electron from the surface of the metal, but also give it enough kinetic energy to reach the other side. And they say what is sometimes you hear or you will see the stop energy or potential needed to stop the electrons. So the voltage that you would apply between these two plates would, like if the electrons are bombarded and you don't want them to get across, so you want to stop those electrons so they don't get through. So the energy needed to stop those electrons is equal to the electron, which is charge times the voltage. It's the same formula that we were talking earlier, that we have used before. Let me see where it is. It's above. Oh, here it is. This formula. So you use the same charge times the voltage, and it gives you the energy needed to stop the electron from getting from one side to another. And then I wanted to show you that, or maybe I will talk about this before, and then I will show you this visually. So threshold frequency, or this frequency that needed to bombard the electrons from the minimum frequency needed to bombard the electrons from the surface, varies with the material. Different materials have different threshold frequency, and therefore they have different work energy or work function. Photoelectric current is directly proportional to the light intensity. So intensity means how many photons are coming. So if there's many photons are coming at the right frequency, so they have to have right energy to be able to pull out the electrons and give it kinetic energy. So if there's many of them coming, so every photons can pull out one electron, right? So the more of the photons are coming, the more electrons will be pulled out. So the kinetic energy of the photon, of the photoelectrons, these are called photoelectrons, is directly proportional to the light frequency. So if the light has more frequency, then some of the energy is going to be used, but more is going to be left for kinetic energy. So the kinetic energy of the photoelectrons will be related to the photon energy that is coming. And stopping potential is directly proportional to the frequency and happens immediately. So this is the stopping potential, V stop, potential energy needed to stop the electrons, stopping potential. And here is an example of how the different frequencies, so the red light has the lowest frequency, the blue light has, or the violet light has higher frequency. So the higher frequency has more energy. So if you see right here, higher frequency will give a photon more energy. So if you have lower frequency coming and bombarding the metal, nothing is happening. It doesn't matter how much intensity you have, how strong or how many of the photons of the lower energy coming, none of them will be able to pull out the electron. But here you have stronger intensity, so not stronger, just stronger energy. So you have higher frequencies. Green is higher frequency than the red one. So you have higher frequency, and with this frequency, it looks like there will be coming a few electrons, right? So there's 1, 2, 3, 4, 5 photons coming and 5 electrons being bombarded. Now they increased the energy, but there's still 5 photons are coming. So just because they increased the energy does not mean more electrons will be coming. More energy means more kinetic energy after the electrons being bombarded from the surface. And another interesting, so that was our photoelectric effect, right, that we talked about. And here is Compton effect. So Compton effect is relationship between momentum of the electron so if the photon or electromagnetic radiation photons are coming in bombarded into electron, the electron might be scattered or freed, and at the same time some of the photon can be released. And here's an example, the X-ray. This is how X-ray is made. So electron has some of the energy and the photon has some more, like another photon, like X-ray. So maybe this is X-ray photon came, different wavelength photon is going to be leaving, but some of the energy is going to be given to the electron. So the energy is mc squared, and if I take mc and times c, it gives me p, because p is the momentum, so mass times velocity, and c is velocity, speed of light. So if I break c into c and c, so I have mc times c, that gives me momentum times c, and also energy of the photon is equal to h times frequency, and frequency is equal to c over lambda. So if I say pc is equal to hc over lambda, I get the momentum of the photon, or momentum of the electron, is equal to h over the wavelength of that electron. So in Compton effects, it's the energy of the light that scatters off the electrons. And scattered X-ray were found to have a longer wavelength. So this one has shorter wavelength, this one has longer wavelengths. Longer wavelengths means lower frequency. So that means part of the energy went with the electrons that was bombarded out. So that's the effect of the Compton effect explained. And Debroglie wavelength. So the wavelength from this equation, you can see that I can rewrite the wavelength is equal to h over p. So they were found independently, these two formulas. So Debroglie wrote it a little bit different. And so if we're talking about the electron may not move with the speed of light because it has a mass. So when I want to find the velocity of that electron that was scattered, I'm going to use the mass of the electron and the velocity of the electron. So instead of p, I have m times v. So many people make a mistake when they calculate the energy of the moving particle using kinetic energy, but you have to use the energy of the this energy of the one that I just explained above, where you have the relationship of h times f, or pc over lambda. So every time you hear Debroglie wavelength, you want to use this formula to calculate the Debroglie wavelength. And I'm going to make different video for your practice questions, not in this one. So I just wanted to do a quick introduction into quantum physics, and then calculations and problem solving is going to be in a different video.